Ever thought about how Google Maps finds the shortest route? Enter breadth first search and depth first search. Every day, billions of people ask Google Maps for directions. You type in your destination, and within seconds, it highlights the fastest route. But here's the thing. Between any 2 points in a city, there are millions of possible paths. If Google tried to check every single one, you'd be waiting forever. Imagine the computational cost of exploring every single connection one by one. It's simply not feasible for a real-time application. So how does it explore a billion intersections and find the shortest route almost instantly? This highlights the core challenge: efficiently navigating vast networks. The answer lies in two fundamental algorithms: breadth first search and depth first search. BFS and DFS are the core strategies computers use to explore networks, whether it's roads, social connections, or game states. Choosing the right one can mean the difference between instant results and wasting hours of computation. Understanding these distinct strategies is key to building efficient systems. In breadth first search, the exploration order is managed by a queue data structure which operates on a first in, first out or FIFO principle. This means the first item added is the first one processed, ensuring a level-by-level traversal. In contrast, depth first search uses a stack which follows a last in, first out or LIFO principle. The last item added is the first one out, allowing the algorithm to dive deep into a path before backtracking. To truly grasp the difference, let's visualize how each algorithm explores the same network. Notice how both start at the same node, setting the stage for their distinct journey. BFS systematically explores all neighbors at the current level before moving to the next level. This ensures that it finds the shortest path in terms of the number of edges, as it always processes nodes closest to the start first. DFS, on the other hand, prioritizes depth. It explores as far as possible along each branch before backtracking. This approach is useful for uncovering a path quickly, but not necessarily the shortest one. Observe the distinct patterns. BFS expands like ripples, finding the shortest paths by exploring layer by layer. DFS dives deep, exploring one branch fully before backtracking, making it suitable for different kinds of problems, such as finding any path or exploring all components of a graph. In this video, you'll learn how BFS and DFS work, when to use each one, and why systems like Google Maps, LinkedIn, and Netflix depend on them to function. So what's actually happening here? Breadth first search, or BFS, explores the graph in layers. It starts at the source, and then it visits all neighbors one step away. This layer-by-layer expansion is controlled by a queue, a first-in, first-out data structure. You add all neighbors of the current node to the queue, then process them in the order they were added. Because BFS explores by distance, it guarantees that the first time you reach a node, you've taken the shortest path to get there. This is a crucial property for finding optimal routes. That's why applications like Google Maps use BFS for unweighted graphs. It efficiently finds the minimum number of turns or intersections to reach your destination. Depth first search, or DFS, on the other hand, takes a different approach. It dives deep into the graph. It picks one neighbor, follows it as far as possible along a single path, and only backtracks when it hits a dead end. This behavior is controlled by a stack, a last-in, first-out data structure, or implicitly by recursion, which uses the call stack. DFS doesn't prioritize distance. Its main goal is to explore the full structure of the graph, often taking long, winding paths. This visual reinforces how recursion and the call stack implicitly manage the diving deep and backtracking process in DFS. As you can see, DFS might find a long, winding path to a target before it finds a shorter one, because it explores depth first. This comparison clearly illustrates that DFS does not guarantee the shortest path, unlike BFS. Here, BFS found a path of 6 edges, which is optimal, while DFS found a path of 10 edges, which is suboptimal. However, DFS does offer a significant advantage in memory usage. The stack only holds nodes along the current path, which is typically much smaller than the entire level that BFS needs to track. This chart visually represents the memory trade-off. For wide graphs, where a BFS layer can be very large, DFS saves memory. Conversely, for very deep graphs, BFS avoids the risk of a stack overflow that DFS might encounter. To summarize, BFS explores layer by layer, which is inherently distance-based, using a queue, a first-in, first-out mechanism. DFS explores depth first, typically using a stack or recursion, which functions as a last-in, first-out mechanism. Crucially, BFS guarantees the shortest path, while DFS does not. Regarding memory, BFS typically uses O of V nodes, where V represents the total vertices, meaning it can be high. DFS uses O of H nodes, where H is the maximum depth, which is generally lower. Both algorithms have identical time complexity, O of V plus E, where E represents the number of edges. BFS is best for finding shortest paths, while DFS excels at exploring the full graph structure. The main weakness of BFS is its potentially high memory usage, whereas DFS's weakness is its lack of distance optimization. Now let's see when to use each algorithm in the real world. Imagine you're building Google Maps. A user enters a starting address and a destination. The graph is the road network. Intersections are nodes. Roads are edges. You need the shortest route, minimum number of turns or intersections. BFS is the perfect choice for this. It explores the network layer by layer, guaranteeing that the first time it reaches the destination, it's taken the shortest path. You use a queue to track which intersections to explore next, and you mark each one as visited to avoid cycles, ensuring efficient exploration. Once BFS reaches the destination, you reconstruct the path by backtracking through parent pointers, revealing the optimal route. Now imagine a different problem. LinkedIn wants to check if two users are connected, whether there's any path between them, no matter how long. Here, you don't care about the shortest path. You just need to know, is there a connection? DFS is more efficient for this task. It dives deep into the social network, following friend connections recursively, exploring one path as far as possible. If DFS finds the target user, it stops immediately. DFS uses less memory because the stack only holds the current path, not every user at the current degree of separation, making it efficient for reachability checks. Finally, consider an embedded GPS device in a car. It has limited memory and might need to navigate millions of intersections. BFS would quickly overflow the queue in such a scenario, demanding too much memory for the device. But DFS can explore the network with a shallow stack, making it feasible even on constrained hardware and avoiding memory issues. So how do you decide which algorithm to use? Start by asking, do I need the shortest path? If yes, and the graph is unweighted, use BFS. If the graph has weighted edges, like real maps where roads have distances or travel times, you need Dijkstra's algorithm, which is a weighted version of BFS. If you only need to check reachability or find connected components, DFS is more efficient. Next, consider memory. If the graph is very wide, meaning many neighbors per node, BFS might overflow the queue. In that case, DFS is safer. If the graph is very deep, meaning long paths, DFS might cause stack overflow. So BFS is better. Finally, think about the problem type. BFS is ideal for shortest paths, level order traversal, and finding minimum steps. DFS is ideal for cycle detection, topological sorting, and exploring all possible paths. Both algorithms have the same time complexity, meaning O of V plus E, where V is vertices and E is edges, but their memory and path guarantees differ. In real systems, Google Maps doesn't use plain BFS. It uses Dijkstra's or A star, which handle weighted graphs. But BFS and DFS are the foundation. Master these, and you'll understand how every graph algorithm works. Whether you're optimizing routes, analyzing social networks, building recommendation engines, or solving puzzles, BFS and DFS are the tools that make it possible.